Welcome to The Explainer. Today, we're going to get right down to the nitty-gritty, the absolute core of how our digital world remembers anything at all. We're talking about registers and counters. These are the tiny, brilliant little circuits that make, well, everything from your phone to a massive supercomputer actually work.
Okay, so here's our game plan. We're going to build this up from the ground floor. We'll start with the tiniest possible piece of memory you can imagine, and by the end of this, you'll see exactly how these simple little parts snap together to create some seriously powerful hardware. All right, let's start at the very beginning. I mean, before you can even think about complex software or super fast processors, you have to solve one basic, fundamental problem. And that problem is this. How does a machine actually remember a single one or a zero? I mean, how do you physically hold on to one tiny piece of information when electricity is always moving? Well, the answer is pretty darn clever.
It's a special kind of circuit called a flip-flop. Now, the best way to think about it is like a digital light switch. You can flip it on for a 1 or off for a 0. But here's the crucial part. It stays in that state. It holds its position until you specifically tell it to change. And just like that, you've created a 1-bit memory. Okay, so storing one single bit is a fantastic start. But to do anything really useful like store a letter or a number or an instruction for a processor, we've got to handle much bigger chunks of data. So the question is, how do we scale this whole thing up?
Well, the solution is actually beautifully simple. We just group a bunch of those flip-flops together. And that's what we call a register. So if you need to store, say, an 8-bit number, you just grab a register made of 8 flip-flops. It's like having a whole row of those digital light switches, all lined up, ready to hold a complete piece of information. Maybe like the result of a calculation happening inside a CPU.
Now, a really important idea with registers is how you get data in and out of them. And you've basically got two main ways to do it. You've got serial, which is kind of like people lining up to get on a bus one by one. It's simple, sure, but it's slow. Then you've got parallel, which is more like a massive highway with tons of lanes. All the bits move at the exact same time. It's way faster, but as you can imagine, it needs a lot more wiring. This is a classic engineering trade-off, right? Speed versus complexity. So by mixing and matching these serial and parallel ideas for input and output, you get 4 main flavors of registers. Each one is built for a specific job. Take a SIPO, for example. That's serial in, parallel out. It's perfect for something like taking a single stream of data coming in from, say, a network cable, and then instantly converting it into a wide format that a processor can grab all at once.
Okay, so registers are awesome at just storing data, holding it steady. But what if we want that data to actually do something predictable? Like, what if we want it to count?
So what does that look like? Let's just watch a simple 2-bit counter do its thing. Right now, it's starting at 00.
And boom, the first clock pulse hits, and it increments to 01. That's 1.
The next pulse ticks, and now we're at 10, which is 2 in decimal.
And one more pulse takes it up to 11 or 3. And that's really all a counter is. It's just a special kind of register that's been wired up to automatically cycle through a set sequence of numbers, moving one step forward with every single tick of the clock.
That total number of states in the cycle actually has a technical name. We call it the counter's modulus. Since our little 2-bit counter had 4 different states before it would repeat, we'd call that a mod 4 counter. And this scales up perfectly. If you used 3 flip-flops, you'd get 2 to the power of 3, or 8 states, a mod 8 counter. The more flip-flops you add, the higher you can count. Simple as that.
But here's where it gets interesting. Not all counters are built the same way. There's a really fundamental difference in how they get that ticking clock signal, and it has a huge impact on their speed and how reliable they are. And this really breaks down that trade-off perfectly. On one side, you have asynchronous counters, sometimes called ripple counters. The domino analogy is perfect here. The first flip-flop changes, which then triggers the second, which triggers the third. It's simple to build, but that ripple delay can cause huge errors at high speeds. On the other hand, you've got synchronous counters. Here, a single clock signal hits every single flip-flop at the exact same time. They all change in perfect unison, like soldiers marching in step. It's definitely more complex to design, but for anything that needs to be fast and precise, it's absolutely essential. Right, so that added complexity means you have to design these synchronous counters really carefully. So let's just pull back the curtain for a second and take a quick look at the actual engineering blueprint for how these things are made. Now, don't get bogged down trying to memorize all these steps. The big idea here is that there's a very specific, systematic process that engineers follow. They start with what they want the counter to do, Then they use these special tools like state diagrams and K-maps to figure out the exact logic. And they finish with a complete circuit diagram. It's this formal process that lets you turn a simple idea, like I need a counter that goes from 0 to 5, into a real, working piece of hardware.
Okay, so we've seen the basic flip-flop, we've seen registers for storing data, and we've seen counters for sequencing. So now, let's look at a component that kind of takes all of these ideas and mashes them together into one incredibly flexible, powerful package.
And here it is, the Universal Shift Register. This thing is truly the Swiss Army knife of registers. It's a total beast. It can just hold data steady, it can shift all the bits to the left, shift them all to the right, or it can just wipe everything and load a completely new set of bits all at once. It's so many different functions packed into one super efficient component.
And how does it do all that? Well, its secret is this little mode control table right here. It all comes down to just two control inputs, S1 and S0. By just changing the zeros and ones on those two little pins, you can command the register to do exactly what you want: hold, shift right, shift left, or load. And it's that incredible flexibility that makes the Universal Shift Register a core building block in pretty much everything, from the CPU in your computer to complex communication systems.
So there you have it. We started with just a single bit, a tiny flip-flop, and we built our way all the way up to this incredibly versatile universal register. It really shows you how these simple yet clever building blocks combine to create the entire complex digital world we use every single day. The foundation is actually pretty simple, but what you can build on top of it, well, the possibilities are endless. So I guess the only question left is, what will you build with them?